Welcome, everyone. My name is Yu. I'm a professor at the University of Warwick, and I'm chairing today's RSS webinar. And yeah, so for this session, we're going to discuss the paper statistical clustering for temporal networks through a dynamic stochastic block model. And this paper is by Catherine Matthias and Vincent Mir. And both Catherine and Vincent are with us today. And also, well, if you've attended the previous webinars, you know that we have this tradition that we also have a discussant, and today's discussant is Patrick Rubin Delange from Edinburgh. So throughout this meeting, we definitely welcome everyone's participation online, but during the presentation, maybe it will be better if we just mute ourselves. And if you have questions, please just leave a comment in the chat, and we're definitely going to deal with that at a suitable time. So this meeting will be recorded, and we plan to post it online on the RSS YouTube channel. And if anyone has any concern, please do let us know, and we will definitely endeavor to edit it out and to suit your purpose. Okay, so basically the timeline for today will be first Catherine and Vincent will do the presentation, and Patrick will do the discussion, and then it will be open to the floor. So as for now, I'll just let Catherine to take over. Let's welcome. Thanks.
Okay, thank you very much, Yi, and thank to the organizers of this very nice webinar. It's a pleasure to be there with you. So I'll do the talk, but Vincent and I are both ready for the questions and answers part, and also with the discussion with Patrick. Please feel free to interrupt during my talk. Maybe either raise your hand. I don't see the end when I'm sharing, but Yi and Patrick will see them probably, or maybe just turn on your mic and ask the question. That's no problem with me. So we've been asked to present this quite old paper now, but still very useful, I believe, which is a model that we call the dynamical stochastic block model that is aimed to do a statistical clustering of temporal networks. So let me present this briefly. I have first an introduction. It's it's directed to a contact network, but of course, when we designed this model with Vincent, we had in mind these contact networks, but you can use the model for other type of networks. So here I'll focus on that type of network, but it's not mandatory that these are contacts. So in our initial idea, we had different individuals that were at stake. It could be humans or animals or species. And the network we are looking at are contact networks. So they could be built from either sensors-based measurements, and we'll see an example of such a dataset at the end of the talk. This could also be declarations in surveys, like you declare you are a friend with that other person. This is more the type of data we have in social sciences. This could be obtained through field observations of association between animals. Vincent and I do work a lot with ecologists, and they have this type of data. So either individual animals or the whole species, like trophic relationships between species. We could have also trapping data, well, a lot of different things in mind. And in this model, we had different aims in mind. One of the first was studying the sociability between those individuals or the ecological processes at stake. And the formal definition of the model we're going to use will be that there are n individuals, which will be the nodes or the vertices in the graph. and we will record either the presence or absence of a contact or an interaction between those nodes, or we can also record a weighted value like a frequency of contact. So the edges between the nodes could either be binary or weighted. And we are interested in dynamic contact networks. So the idea, and that here I show a small typical figure, is that we have a set of snapshots of these networks recorded at different time steps. This could be hour, day, week, season, whatever. The idea is that the time steps should be equally distributed. I mean, if you have a very large difference in the different time steps, then maybe the model might not be appropriate, but we can discuss that if you want. And we also had in mind to study animals, and so they would die or give birth across the different seasons we were looking at. So we wanted the model to account for the individuals maybe present or absent at each time step. So obviously, if we want to do a longitudinal analysis of the dataset, there cannot be a complete turnover in the individuals during the different snapshots, but we can allow for a certain for a certain variability in the presence of the nodes at each time step. So we have t different time steps, n sub t individuals at each time step, and the total number of individuals in total n should be quite small compared to the sum of the entities, meaning that most of the individuals, a vast majority of the individuals, stay present during this longitudinal analysis. Otherwise, it's not appropriate. Okay. And then, as I already said, the signal of the interactions that you record, it can either be binary, you record the presence, absence of an interaction, or it can be weighted also. The questions we wanted to tackle with the model I'll discuss in a minute is mainly about social structure. So we wanted to understand if there's a peculiar non-random mixing of the individuals that would be a sign for a social organization. And if there is a social structure, we wanted to understand what is the dynamics of this social structure. We could be interested in other questions such that, for instance, this social structure vary with other factors like seasonal changes, breeding, response to stress, etc. And we could also be interested in something more ambitious, like can we predict, for instance, how infectious diseases can spread on our data, on our networks. But okay, here I will mainly focus on the first two questions and not discuss the other ones. And the way we did that is by providing a model that where the first aim was to move beyond descriptive statistics and proposing a statistical model for the organization of these networks. And so the idea was to rely on a clustering of the nodes to capture a social structure on the individuals if there's one such a social structure in the data. Okay, now let me discuss a little bit clustering dynamic networks. What are the challenges at stake? Clustering dynamic networks is a little bit different from clustering static network, mostly because of the label switching issue. So when you're looking at just one network, say the one on the left here, you all know that the groups can only be recovered up to label switching. And if you do cluster those two graphs independently, which are two snapshots of a set of relationship evolving in time, then if you do that independently, you can have different label switching at different time step. And in this representation, for instance, you would say that, okay, all the blue nodes, or the vast majority of the blue nodes, they became yellow at the second time step. So is it indeed the case that they became yellow, so they changed its group? Or is it rather that there's a label switching between the blue and the yellow group? That's the issue to solve here, and it's quite a challenging issue. And what we wanted to do is really follow the evolution of the cluster through time, and that's why it's not sufficient to cluster the graphs separately at each time step. So our goal is that smooth recovery of the clusters across time. And okay, here in that picture, which is quite simple, it's a toy example, of course, you could say, okay, I will set up the label switching so that the vast majority of the groups, they don't change, the vast majority of the nodes, they don't change group through time. So I will say that, okay, the yellow and the blue group at the second time step, they were switched. But in fact, we wanted to do that automatically in a more statistical way, say. So what we did is that we proposed that dynamic stochastic block model that I will detail in a few minutes. And in the model accounts for either directed or undirected graph. This is important because depending on the data at stake, you might want one or the other. And as already said, the graphs can be binary or weighted. And we wanted the groups to be able to change through time. So each individual belongs to a certain group at a certain time, but at one another time it can change group. And also the model parameters may change through time. This means that the blue group, for instance, it's not mandatory that it's always a community group. So a community group would be a group with a lot of intra connection inside the group and low interconnection probability. And so we didn't fix that. So communities can become a peripheral group at another time step. And if you allow that, which is the most general case, then you have to put small restrictions on the parameter value, because then you mix everything. So in the paper, we have a careful discussion about identifiability conditions that we need to put on the model so that we can both allow group and model parameters that change through time, but in a sound way. And then with that model, what we did is that we proposed a variational EM algorithm to infer the node groups and the model parameters. So VEM algorithm has become quite a very classic tool in the statistical community for studying stochastic block model nowadays. And we also designed a model selection criteria. So it's of the ICL type. ICL is for integrated classification likelihood, and it automatically selects a number of groups when you have no idea of what to use on your data set. So let me describe a little bit more in detail the model. Here I start with just one graph and I describe the stochastic block model. So I presume most of you already know that, but let me recall it anyway very briefly. The stochastic block model in the binary case is a model for just a single graph. So here you have this graph with say n equal 10 nodes, and you want to cluster the nodes into 3 groups, which are represented by colors here, but you don't see the colors at first, okay? You want to find those colors on the nodes. So you have a latent variable, which I call here ZT, which represents the color or the group of the node at time t. So you have Z, I, T are IID variables with values in Q different groups. They are not observed, so they are latent. And what you observe is either here in the binary case, you observe the presence absence of an edge at a given time, and you assume that conditional on the cluster's value, so conditional on the latent variable zit, the presence absence, so the indicator of an edge being present, that I call y here, yig at time t, they are independent random variable with Bernoulli distribution here because it's binary, and the parameter value beta both depends on time t and on the cluster zit and zgt of the two nodes I and g that are going to be linked. So that's the binary SBM, and very rapidly it's quite easy to generalize this to the weighted case, where you either observe a true zero, meaning no relation between the two nodes, or you observe a value, say something real that is not zero, or it can be even a vector if you want, a vector of features describing the interaction between node I and node j at time t. And here we model this distribution, the conditional distribution of such a random variable, still conditional on the latent group. It's given by a mixture between a Dirac mass at zero. So the Dirac mass at zero enables us to have sparse graphs, I mean non-dense graphs. So all the edges are not necessarily present. And the beta value here is the sparsity parameter of the graph. So the larger it is, the sparser the larger it is, the less sparse the graph, sorry. And there's an additional parametric distribution whose density here is called F, with a parameter value that I call gamma, that describes the weight that you put on a present edge. Okay. So that's it for the static stochastic block model. And if you want to put dynamics on that, then the simplest way is simply to put a Markov chain on the latent variables. So here, across individuals, we modeled all the individuals are independent and identically distributed random variables. And across time, each Zi is in fact a stationary Markov chain with a transition matrix pi. So you see here the different the ZIT that describes the cluster of node I at time t will form a Markov chain in time. And the goal was to infer the parameters of the model and recover the cluster and follow the evolution of the cluster through time. That's really important. So all this has been implemented in this package. That's an R package called dynsbm. In the package, we have so I already said that, but just to recall, the underlying algorithm is a variational EM algorithm. It infers so the groups and the model parameters, and it's combined with a model selection criteria. So you can ask the package to tell you what's the nicest number of group in your data set. And I mentioned here that we've shown in another paper that this VM algorithm, in that context of the dynamic stochastic block model, it's consistent when the data size goes to infinity. So I won't give any details about the algorithm, and I'm not showing any more math because I don't have time, and I want to show you rather the results first on simulated data, and then on a real data set I will show the type of outputs that can produce the package. So first, we tested the clustering performances of that model, and we used two different indexes. So there's a correct index to be used in that setting, which is what we have called the global adjusted rand index. So it takes the whole classification ZIT through all the nodes and through time, and the adjusted rand index is just a measure of how much your classification is correct. And when it's close to 1, it means that you have a nice classification. And in the literature, when we did that paper, other authors had used what is an average IRI, meaning that they had computed the adjusted rand index at each time t, and they had done a simple average over time of those values. And the problem is, if you do that, is that the adjusted rand index, it's made to account for the label switching issue. So here you account for the label switching issue at each time step, and then you average over all the time. So you're cheating, because if there's a label switching issue between the different time step, and if you don't follow correctly the clusters through the different time, then you won't see it with that measure. But we kept it for comparison, arguing that it was not appropriate, of course. So what are the simulations that we did? Very simple ones, just a toy example to see that it works. It's a proof of concept, say. We considered binary graph, quite small, with 100 nodes only, and time step either 5 or 10 time step, and we replicated those data 100 times. And so we mixed the scenarios with Q equal to 2 latent groups, so 2 clusters in the dataset. And this is the pi here is the matrix of the transition matrix for the Markov chain, the underlying Markov chain. And we took 3 different values from low stability to high stability. So what you see here in PI, you have the 0.9 value here that tells you that you stay most often in the group, and you will change group only with a probability of 10%. So that's very low. And here in the pi low, you change group quite often. Okay. So the scenario will be less easy. So the easiness decreases in with the pi low, and it increases with the pi high. And similarly, we consider different scenario for the connectivity parameter beta that tells you how to connect the group. And here in the low easiness scenario, say we have 3 values, 0.2, 0.1, and 0.15, that are very close to each other. So it's quite difficult to distinguish the groups when you have so close values. And in the medium plus scenario, then you have more space to distinguish the clusters. So that's the kind of result we obtained here. So in the first row, you have the experiment with 5 time steps. In the second row, you have 10 time steps. And from the left to the right, in each of the sub graphics and also inside each graphic, you have the easiness that increases. And these are the box plots of the adjusted rand index. In yellow, the global measure, which is the correct one, and in gray, the averaged one, which is not appropriate in that setting, but we computed it anyway. And what you see is that when the scenario is quite difficult to do, so mainly on the left part of the screen, then you have adjusted run indexes that are quite small. But when the scenario becomes more easy, when the clusters become detectable in some sense, then you obtain a very large adjusted run index that are very close to 1. And here, so I didn't discuss this last scenario, which is medium with affiliation. It's a particular scenario, but let me just mention here that you see that the yellow measure, which is the correct one, it's quite poor. So you have data sets where you don't recover the clusters, while the gray one tells you, okay, you've done a perfect job. So that shows that the gray measure, the average adjusted rand index, is not appropriate because it does not capture the fact that here you're missing completely the label switching issue between the different time steps. So we also tested the ICL, and this was okay. So we tried to recover 4 groups, and in our experiments, most of the time we indeed recover 4 groups, and sometimes the experiment told us, okay, select 3 or 5 groups, and what happens is that when we select either 3 or 5 groups, this is because the clustering we managed to get was quite poor and had a small adjusted rand index with respect to the truth. So in general, the ICL criterion is doing a good job. Okay, let me finish. I have a couple of minutes to finish with this real data set to show you the kind of outputs you can obtain with the package. So here we took a quite classical data set, I think, from the Social Patterns website. It's a record of face-to-face encounters between high school students. So they were wearing these sensors, and anytime they encounter each other during 4 days, the sensors recorded an interaction if it was more than a threshold of seconds, say. Okay, and there are 27 students, so I already said 4 days. And we decided to discretize the data set. So we have frequencies of interactions, and we discretize the data set with 3 bins. So we have 3 different values for the interaction. And the ICL criterion in that data set selected 4 groups. Okay, here is one of the outputs of the package. You can see the 4 days, which are Tuesday, Wednesday, Thursday, and Friday, the 4 days of the experiment. And you see the 4 groups, 1, 2, 3, 4 here, and you can see the flow of the students in the groups. So for instance, here you see that from day 1 to day 2, the group 2 becomes part of the group 2 goes into the group 4, and the other way is that from first day to second day, part of the group 3 becomes group 1, for instance. So you can really follow the individuals like that. So there's no individual following. I don't know if you see my mouse. But here, for instance, you cannot say that those individuals that arrived the second day in group 4 are exactly those that leave the group 4 and go back to group 2. Okay, this cannot be read like that. So just beware about this flowchart, but these are quite interesting. And we output also an estimation of the parameters of the model. So here you have the transitivity, the matrix of transitivity, the connection between the 4 different groups. It's an undirected graph here, so we show just the upper part of the matrix, and the width here of those bar plots indicate the sparsity, so the beta parameter, so the sparsity of the model. So the larger these bars, the most interactions you have in the data set. So here what you can see is that, for instance, group 2 is a community, group 3 is also a community, and you can discuss the other values of the interactions. And for instance, what we obtain on this data set is that, okay, group 2 and 3 are communities. We have respectively 3 and 4 individuals who permanently stay in that group, and we call them social attractors. Group 4 is also a community, but it has much less intragroup interaction. Group 2 and 4, we've seen that in the flowchart, they exchange students, and group 1 is stable with a low rate of interaction. And then we wanted to cross this information with gender that was not used in the analysis, but we've done an a posteriori crossing info with gender. And we noticed that in fact group 3 has only male students, and group 1 has a backbone of female students that remain in the group for all the experiments. And so females are less likely to change groups than males, at least in the dataset, with a vast majority of females belong to low interaction groups 1, 4, and they do not switch between those groups. Okay, conclusions. So with that model, the dynsbm, we propose to reconstruct the evolution of clusters in snapshots of graphs through time. We control for the label switching issue between different time steps. We can model binary or weighted dataset, and you can have a model selection performed through a criteria. So there's this R package dynsbm that recently was updated on the cron because we were asked for it, so we did that. The paper was published in GRSSB in 2017, so quite a while now. And I mentioned there's also a companion paper that we wrote mainly for ecologists in the Royal Society Open Science. Thank you for your attention, and I'm ready for your questions. Or maybe first the discussion, I think.
Yeah, you are indeed right, Catherine. Thanks very much for the talk. So maybe Patrick, are you going to share some slides or just going to?
I have some slides. Is it my turn now?
Yeah, indeed.
Yep. Okay. Let me get this up.
Well, while Patrick is setting up, there's actually a quick question from the audience. I don't know, Catherine, if you want to just have a quick clarification.
If there's one, why not?
Yeah, so there's one asking what you mean by smooth recovery of the cluster. It pops up at the very beginning of the talk.
Yeah, indeed. So that was this idea of we have the transition matrix to model the transition of the nodes between cluster. We don't want to authorize random changes, completely random. So the way we smoothed the clusters is by putting this Markov chain as in the model. And okay, you can always do another choice, but then the interpretation would be different. That's all. So you have to decide something. Hope that answers the question.
Thank you so much, Catherine. Well, since Patrick is ready, maybe we should just let Patrick go first.
Okay.
Great.
Thanks. Sorry for the delay. I had it working perfectly a half an hour ago. I don't know what happened. Well, of course, I'd like to start by thanking the organisers for the honour of inviting me to comment on this paper. It's a paper that was, I think, very important in the dynamic network analysis. And I mean, it does a number of challenging things, but actually one of the things that it does very simply and very nicely is to highlight this problem of identifiability when you're trying to estimate communities in a network over time. So this identifiability problem is what I'm going to talk about most. But before I go there, I just wanted to make a few sort of other supportive points. The authors are clearly sort of have as an application focus contact network analysis. So that's networks where an edge represents some sort of contact, maybe even a physical contact between individuals or animals, and I gather that they're thinking about social science and ecology. But almost 10 years down the line, I think this problem of estimating community structure and dynamic networks is very, very topical and has a huge number of applications from disinformation, various things of security, so software security, cyber security, forensics like fraud detection or corruption or policing, neuroscience, of course, and then there's this emerging field of mechanistic interpretability and AI safety. So you can find many papers now trying to find clusters of neurons, for example, in large AI systems, such as LLMs. And of course, dynamic networks serve as a very good data abstraction for generic unstructured data. And I think in all of these problems, you can find many papers that are trying to find dynamic clusters in networks. So it's a really important area and problem. And again, just before I go into the more specific points about identifiability, of course, it has to be acknowledged that scale in a lot of these applications will be a considerable complication. So I don't want to talk about this now because it's such a vast topic. And there's so many different approaches from things to do with spectral clustering. So my research group has done a lot of that, but also many larger research groups. So Carrie Preeb and all his collaborators, for example, and people like Jesus Arroyo or Joshua Achtenberg. There's people doing various sorts of tensor decomposition for these problems, including Andrew Zhang and Yi Yu, the organizer of this session, and many other people. And then there's a whole field of graph neural networks. So it's vast and it's complex, and there's loads of efforts going on to try to achieve dynamic clustering in large dynamic networks. It's something that has to be highlighted as a problem. For example, if you're hoping to use the author's method for these very large networks, because I gather that they can only handle a few hundred or a few thousand nodes, right? So I just thought I'd say that, but really what I want to focus on more is this very interesting and very complicated problem of identifying communities evolving through time. Right? So I've taken the liberty of changing the notation a little bit, just because I don't need the full generality that was in that paper, but it's still hopefully recognizable and standard. So B is your matrix of intercommunity connection probabilities, right? So that's, if you've got K communities, B is K by K. Z1 up to Zn are the labels of each node, so telling you which community each node belongs to. And both of these things are evolving through time. And the paper makes the very important and striking observation that if you're allowed to have both B and Z varying arbitrarily, you can you can encounter really enormous identifiability problems. Catherine presented some interesting examples, but actually, if you think about it, you can just have two stochastically identical time steps, so that the right answer, sort of intuitively speaking, should be that none of the nodes have changed community. But actually, if you're allowed to change B and Z, you can find that you can explain this with all of the nodes changing community. So it's if you're really free to just move B and Z, then you have terrible problems. And it could be easy at first glance to dismiss this as a trivial problem, but actually today this problem remains significant and a continued source of confusion. I won't, because of course it would be a bit unkind, but there are many papers kind of coming out in the last few years that have essentially got completely lost with this identifiability issue. And many other papers that have done really quite deep maths to try to sort of solve them, right? So especially in sort of adjacent areas like graph matching, Bayesian inference, when you have a graph that you're trying to treat as unlabeled, the whole area of inductive representation learning, graph neural networks, and and many more. So it really is a very big problem. And the solution that's proposed in this paper is quite simple, and it's quite interesting, which is, if I understand it correctly, to assume that the intra-community probability for a particular community is fixed through time. And moreover, that if you have two communities, that each of their intra-community probabilities is distinct, right? So I think this is a correct operational interpretation of what's written in the paper, but I'd be glad to hear otherwise. So I agree completely with a mathematical and technical claim that identifiability is resolved under those assumptions. What I'd like to ask the authors about is the scope for extending this to slightly more realistic models of community structure. And in particular, the thing I want to highlight is this model called the degree-corrected stochastic block model. I imagine a lot of people are familiar with it. So what does it say? Well, it's the same as a stochastic block model, but each node now has a weight, right, which drives how many connections it tends to form. Okay, so Wi, if it's large, means that node I will tend to make much more connections, right? And just so you understand the papers that the pictures that I'm about to present, if you spectrally embed a graph which follows a DCSBM, what you'll see, right, instead of a bunch of K clusters, which is what you see if you had a stochastic block model, is you'll see K rays, right? And they're all rays kind of emanating from the origin. And how far along that ray you are reflects how popular you are, how many connections you tend to make. So this is a toy example that we published in Series B a few years after your paper, which is the enmity network of Harry Potter characters, and this pattern here is exactly what you expect under a two-community degree correct stochastic block model, right? So you have these two rays, right? You've got the red ray and you've got the green ray. These are the, if you know the story, these are the good characters and these are the bad characters. And then if you look far to the right, you've got the characters that are somehow prominent in the story and they make loads of connections, right? And same if you look down to the right for the green cluster. So that sort of pattern, just have it in mind. Something a little bit closer to the applications you're talking about. This is a data set, a visualization that we published in NeurIPS in 2021. So now it really is a dynamic network. It's got it's a contact network, so it's primary school students. They're wearing a sensor, and if they interact, then basically you get an edge between them. And we've used unfolding here to get sort of fairly stable pictures over time. And again, you see these really very sort of distinctive ray-like patterns, right, where each ray corresponds to a community, where in this instance, a community is a classroom, right? So even closer to the sort of examples you're thinking about is one of your own data sets, right? So I just picked this from your package, I think you said you recently updated. So it's a little bit less clear cut, but again, you know, if so, this is the network of ants. I picked the one of the most nodes. You look at this pattern. It's you know, it's just a picture, so it's not statistically significant, perhaps. But again, you see what really kind of looks like degree variability in the communities. You know, so you have a ray coming out here and a ray coming out here, and once you've seen other pictures that look a lot like degree-corrected stochastic block models, again, you sort of suspect that maybe there's some level of degree variation going on here within communities, even in the examples you're looking at. So this is a point that was raised by one of my students some time ago as a really kind of striking point and a quite frightening point, perhaps, which is actually, if it is possible that in all of the graphs that we've ever, as a community, presented, real-world graphs in papers, in statistics, it's possible that none of those real-world graphs would actually pass the test of being SBMs rather than DCSBMs. Certainly every graph that I've looked at has quite clear-cut signs of degree variation. But of course, I don't claim this as a fact, but it's just a possibility. And so I was wondering if the authors had put any thought or had any sort of new ideas about how their identifiability solution might be extended to allow for this sorts of to allow for degree variation, so dynamic DCSBMs. And that's the main sort of question I want to ask. But if you'll forgive me for making slightly broader claims, well, first I want to commend the authors for making such an important contribution to the field of dynamic network analysis. I think 10 years down the line or almost, dynamic network inference remains a significant problem with clear scientific and societal implications. I would claim that language and practice around dynamic network clustering, dynamic latent position network models, embeddings continues to be really misleading, limited, and underdeveloped. And I think this paper was kind of really significant in providing an early warning about the sorts of problems you could encounter. But actually, thinking about the sorts of dynamic networks that really have major world implications, I am not sure if any of the solutions right now are sort of practical for those real world problems. But that's all. Thank you.
Thanks very much, Patrick. I don't know, Catherine and Vincent, do you want to?
Yeah, sure. Thank you, Patrick, for this very nice discussion. I took some notes and I would like to reply to that because I found this very insightful. First of all, I would like to stress that the remark you made about the scaling is really, really important. And in fact, it is true that that package, it can handle like maybe thousands of nodes, but for sure it cannot go to millions. And that's a problem with those statistical methods like the VEM algorithm. They are okay for, say, a small to moderate size data sets, but not to very large data set. But okay, it's fair in some sense, and the people we work with, at least in ecology, they do have very small data sets. So for us, it was not a problem. But it's true that it's really a limitation. Then I'd like to discuss the identifiability we proposed in the paper. You are quite right, but not exactly. So what we proposed, we had two proposals in the paper, one main proposal and one more hidden somewhere. The main proposal was to ensure that, so you have this diagonal matrix that you call BT that tells you how the group K will connect with group L at time t, and we say, okay, there's something that should be fixed through time in that matrix, and we decided to fix the diagonal. So we impose that BKK stays constant through time. But we did not impose that BKK would be different from BK prime K prime. And this is, I think this is not even, so we had a proof of generic identifiability, that's true. That doesn't point exactly the restrictions on the parameter matrix that you need, though you know that they are of dimension smaller, which is okay generically, but we didn't put exactly to the set of restrictions. But I believe that if the case row is different from the case prime row, then you could have, for instance, two groups that have the same intragroup connection, but they are distinguished by the way they connect to the others. So the K row and the K prime row, if they have different values, which is mandatory to distinguish the K group from the K prime group, then that should be sufficient, at least in theory. And we had a second proposal that we thought maybe would be more specific, and the proposal was to decide, okay, you pick any group, say for instance the first group, and you decide that this row and this column, if it's undirected of course, this row of parameter values stay constant through time. So that's also a possibility. You say, okay, the group one it's my pivotal group in some sense. The way it connects with the other ones, that stays constant through time, and then I can resolve the label switching issue between groups and clusters that can move, blah blah blah. Okay, then let me switch to the discussion on the degree corrected stochastic block model. I think this model is really interesting, and I never worked with it because it happens, but I really think it has a lot of possibilities. Though I would say it's not something that can replace the SBM, it's something complementary. And let me argue. I think that people that work with the degree community, degree corrected SBM, they focus on communities. So for me, communities are particular groups where you have a high intraconnectivity and a low interconnectivity. Okay, and so if you want to recover communities, it makes sense of not looking at the degrees, because this is a noisy signal for you. But if you want to recover clusters without any a priori on the clusters, on the form of the clusters, then you should not use degree corrected SBM, because for instance you could want to recover peripheral nodes, which are low degree nodes. So Vincent, please turn on your mic and complement what I'm saying.
Yes, that's exact. In particular, when you are studying social interaction, you may be interested by these social people that are at the boundary of the social group. So it might be this group that you are interested in. And if you are focusing on community structure, that's exactly what you do when you do spectral clustering or when you do degree corrected SBM. So we do think that this is a nice solution when you are interested in community structure, but for us, we would like to be more flexible in the kind of structure we may find. So I have a particular example. We add a little trick to this model to handle bipartite networks, and in particular plant pollinator networks. And in the end, we find a very, very interesting structure, which is core periphery structure in these plant pollinator networks. And then, by essence, it was not a community structure because it was gathering plants and pollinator inside a group that is somehow a rich club structure, a lot of nodes connecting between themselves, but also many plants and pollinators that are in peripheral groups. So this might be the reason for us not to use or not to develop more on these degree corrected SBMs.
Okay, maybe I'll continue answering the points raised by Patrick. Then you had this sentence, so maybe I misunderstood. You said, okay, I believe that a real world network would not pass a test of being a SBM rather than a GC SBM. For me, that's not true, because well, as we said, using a DCSBM is a modeling choice that makes perfect sense, but I wouldn't say that. So I think such a test does not exist, or I'm not aware of it. And if such a test of goodness would exist, I would not bet that you would not pass the test of being a real SBM instead of a DC SBM. For me, it's a modeling choice rather than a goodness of fit question. Please, Vincent, go ahead.
No, also about the feasibility of the estimation of the parameters on large networks. So there is no debate. It's not feasible. I mean, above thousands of nodes, there's no way we can use this kind of models, and that's the end of the question. Of course, 10 years ago, this was the beginning of the machine learning based methods like all these not too vague or embedding based methods. And this is definitely the solution that is adopted at the moment to project nodes in an embedded space. And okay, this is another story. This is completely different. This is less, I would say this is less written. You have less formulas, or you don't have these nice random variables, but this is working in practice. So I would say this is two branches of the same tree, but not the same branch.
We're doing cophylogeny also sometimes. Phylogenetic trees, you have two branches and they diverge, obviously. But we try to reconcile them sometimes. Okay, and about your last question about identifiability of a GCSBM, well, I have to admit I have no idea, but that's a great challenge to try to to solve such a question, but I wouldn't dare giving a response like that right now. I'm finished.
Patrick, I don't know if you want to say something more. Or...
I don't know. Is it protocol that I respond? I've never done one of these things.
What do you want?
Maybe I would have to be given the opportunity to think a little bit for a few minutes.
Yeah,
sure. I don't know if you want to.
Sure, of course. Catherine and Vincent, there's I think a clarification question from the audience. I guess it's probably a comment about computational complexity. So I don't know if you still remember that detail.
Yes, there is something quadratical in the number of nodes somewhere in the algorithm. So this is the reason why you can't address big networks.
Yeah, so while we're waiting for Patrick to organizing his words.
Yes. So how am I supposed to think when you make comments like this?
Yeah, maybe I just ask some questions. So first, thank you very much for all the very interesting discussions and then the presentation. And it's actually one of the audience asked about this smooth change. So I guess okay, because I work on change point a bit, and I guess the other one is the abrupt change, but I think your model can actually handle both, right? So when you say smooth, it's not really on the opposite of abrupt. So
No. And in particular, I believe it would be interesting to do like change point detection for the Markov chain modeling. Maybe looking at one additional latent random variable for the whole graph and putting a Markov chain on it and saying, okay, there are some phases of the time during which the networks behave in some way, and then you have another physical behavior that happens. So by putting this additional Markov chain on top of everything, you could distinguish phases that can be interesting, I'm sure, in many applications, but we didn't face it yet because it didn't occur to us to face those problems. So, but yeah.
Sure, of course. Thanks very much. Okay, I just want to remind the audience while the floor is open to everyone. Please feel free to unmute yourself or just make a comment, and we can read out. Yeah. Okay. So maybe I have one more question / comment, and this is related to what Patrick talked about identifiability. I think there might be slightly different issue here. So maybe Patrick, what you are thinking is probably this vertex correspondence issue. So when we don't really have labeled vertices nodes, and we do have a sequence of networks, how we are really matching all these observations. I think that's an issue. And the identifiability issue Catherine and Vincent address in their paper is more about the parameter identification. I think both are very important, and they probably
no. I don't. Well, I know that there are some situations where, as you say, you have two or many graphs that are there's no correspondence between the nodes, right? So that's now of course is very difficult because you have a graph isomorphism problem on top, right? I guess my claim is a bit sort of it's a bit elaborate perhaps, but my claim is that in a way, if you've got communities that are allowed to sort of like switch without any sort of restriction, in a way you kind of have that problem. Like it becomes a graph isomorphism problem in disguise, right? Because there's nothing to stop you from just and I think that truly solving this identifiability problem, even in the one they're looking at, even for the SBM, as soon as K, for example, is a little bit large, you're not going to be able to always avoid this isomorphism problem. If you don't mind, so I thought there's just two things I wanted to maybe two thoughts I wanted to give perhaps in response to Vincent and Catherine. So one of them, Vincent, is you were speaking quickly, so I'm not sure if I'm not sure if I interpreted it correctly, but when statisticians talk about spectral clustering, or spectral embedding, I think for the most part they're talking about an algorithm for estimating the stochastic block model or extensions. So it is very much a model-based endeavor. It's not the same as the spectral clustering of a year 2000, which had no connection to a model. It was really just presented as a best low rank approximation, say, for example, in the Frobenius norm, say. So I wanted to make sure it was clear, and it's the same also for people doing kind of tensor decomposition work. I mean, there's a long history of people doing tensor decomposition in a purely computational algorithmic sense, but I think probably many of the statisticians that I was referring to are doing modeling using tensor decomposition. So they view the tensor decomposition as an algorithm to fit a model, which will be something like a stochastic plot model.
Patrick. So to speak slowly and to explain what I was mentioning, to what I knew, and it was probably wrong. What the connection between the stochastic block model and the spectral clustering was in the case when you want ISBM for community structure. So this is what I knew. So it might be wrong, and this was the reason why I was saying this.
Oh, as opposed to other sorts of what I guess I don't understand what you mean by SBM for community structure.
So I think this is not exactly correct, Vincent. I think that there are no proofs that spectral clustering is consistent on the stochastic block model with no constraints. So what he means is putting constraints like intragroup connection must be larger than intergroup connection. You have a diagonal of values that are higher than the rest of the matrix.
I see. That's what you mean by community.
But this is not the case. But just
no longer.
To continue on that, Vincent also mentioned spectral embedding, like node2vec. And then when you look at spectral embedding, this is really you're far away from the stochastic block model. So this kind of new methods to embed the nodes of the graph in a vectorial space and then do whatever clustering you want, classical one. This is maybe more scalable to the size of the network, and this is far away from the stochastic block model, I would say.
Yeah, so yeah, no, I completely agree with you that methods like node2vec and deep walk and so on are, well, I don't know. I mean, I think I gather that some people have tried to come up with statistical theory to understand these things, but I don't know what the status of that is, and possibly these tools are maybe not appropriate for scientific applications where you really want to understand the communities and the clusters that you're discovering. I don't know.
Hi everyone. I just want to say thank you so far for presenting. We have reached the hour, so if we have any maybe final comments or anything to wrap it up, or any final questions from anyone still in the audience.
You're fine. Your mic is.
Yeah, sorry, thanks. Let's jump to the audience. Any questions from the audience? Well, if not, I think Patrick, Catherine, Vincent, all the information, all the contact information is available online, and we definitely welcome all the follow-up discussions. I enjoyed a lot for this one. And thank the RSS, thank Anna for the organization. Thank you very much.
Thank you all. Bye-bye.
Thank you.
Thank you.
Bye.